Okay, welcome everyone to this week's Philosophy of Physics seminar. We're very happy to have here speaking to us today Quentin Vigneron, who is a theoretical physicist working in cosmology and topology and the non-relativistic limit and other things close to our hearts. So Quentin studied in the University of Lyon and now has two affiliations, one at the Nicholas Copernicus University in Poland, but also in Lyon. He's here till the end of next week if anyone wants to talk to him in the coming days. So, over to you, Quentin. Thanks very much.
Thank you for the introduction, and thank you for the invitation here. It's the first time I present in the Faculty of Philosophy, so I'm very glad to be here. So, what I want to advertise for this presentation is this modification of general relativity that you can see here. And at the end of this presentation, I hope that I will convince you that it is an interesting modification to consider. And I will also make sense of this graphic here that is a way of understanding that modification. So this is the current ramification of this theory, published one, where there is one motivation and some applications for black holes and cosmology. For this talk, I will only focus on what is the motivation for adding that term in the Einstein equation, and I will quickly discuss the cosmological consequences at the very end. So that modification is related to the topology of our universe and to the field of cosmic topology that studies that the topology of our universe. So I first introduce that field in the standard model of cosmology. What do we mean by a topology of the universe? What is the current observational status, and some mathematical subtleties before I will go into this field. Okay. So the cosmic topology is the study of two things in our universe: the shape and the global curvature. The global curvature is this parameter omega k that is present in our expansion law and that can have like different signs, like so 0, positive or negative. Because it's present in our expansion law, then the expansion of our universe behaves differently depending on the presence and the sign of that term. For instance, in the case of a positive curvature, we have this usual recollapse, a big crunch of the universe. In the standard model, then we say that we can describe three types of universe depending on the sign of this curvature that we call Euclidean, spherical, or hyperbolic. And most of the time, it's considered that these correspond to a single possibility. But this is actually a restriction to generality, in a sense that we forgot the second possibility, which is the shape here, and which corresponds to the fact that for each of these possibility, for our curvature, we don't have one single possible global universe, but the whole family. And the different possibilities within this family are characterized by different periodicity, different shapes that tile these spaces. So for instance, in this Euclidean case, we could have a universe which is so here it's in an analogy in 2 dimensions, a square, which is periodic, and that periodically tiles this space. Or we could have an hexahedron, for instance. And so the three possibilities for the value of our curvature actually do not point towards a single possibility for our universe, but the whole family. This is here a 2-dimensional representation. What in reality we would see in 3 dimensions is because of the periodicity of the universe, we would see exact images of a single object in different positions in the sky. And the distribution of these images, here I just considered one Earth at the center of our universe. The distribution would characterize both the curvature and the precise shape. So this is what in reality we would see. What is behind this is this mathematical structure that is represented here in 3 dimensions. To give you maybe a bit more understanding of what's happening in this hypothesis, we can go into a simulation, which is from the same software that created those images here. where here I consider the universe, which is flat, it's Euclidean, but rather than being infinite, it's finite, and the shape is a cube. And in that case, that cube is periodic. And I put in the center of that universe the Earth. So I said so here we see the moles of this periodicity, which are not physical, they are just mathematical artifacts. So we can remove them. And if we remove them, we see that actually visually we would observe identical images of the same object. They are not different objects, but the same object, like can mirror images. And so we could move eventually in this universe, and this is what we would see. In reality, we would not see like identical images of the Earth, but rather of galaxies or clusters of galaxies. And if we change the shape, for instance, for a dodecahedron, this is the kind of image we would see. So you see that, so in that case, we are in the second family of universe, like spherical with a positive curvature. So strange thing happen, and the distribution of those images is very different. So it's a lot of RAM, so I will remove it. Okay, going back to the presentation, which is still pixels, but no problem. So, okay, we have these two concepts, global curvature and shape. And here you could say, okay, but I never heard about this possibility of having this periodicity. It seems a bit exotic. And why don't we consider it actually in the standard model? And the answer is that first, it's not an exotic hypothesis. And second, it's actually implicitly assumed in the standard model. And the reason behind this, the reason why the standard model, specifically in the flat case, is not a model of an infinite universe, is because in any realistic cosmological model, in a sense realistic that not strictly speaking homogeneous, but where we have some inhomogeneities to describe the structure formation, cosmic microwave background, etc. To solve mathematically, to give a prediction for those inhomogeneities, we need to solve some elliptic equations. For instance, in the Newtonian case, we have this Poisson equation. In GR, it's the Hamilton equation. And the moment we want to solve an elliptic equation, if we want it to have a solution which is unique, we need to assume some boundary conditions. And the only one that is cosmologically realistic is the boundary condition where we actually consider a finite volume, but without boundary, which exactly corresponds to considering basically a periodic universe. Now, it's not a problem. We can always consider that periodicity to be way bigger than what we observe, and so we don't care about which shape we considered. But implicitly, for our mathematical model that describes our universe to be well-defined and have unicity, then we always assume this possibility, these periodic conditions. Okay. So this is the description of the possible topologies we have for our universe with respect to the standard model, where we have an isotropic curvature and we have three different families with the sign of the curvature. This is a restriction with generality. And for this, I need to describe a bit more mathematically what I mean by topology. And this will be the last let's say, piece of mathematical information I will present before going into the very subject of this presentation. I forgot, before generalizing the mathematics, what about the observational status? Because you could say, okay, it's nice to have these two concepts of curvature and periodicity, but what about observations? Again, a lot of pixels. Regarding the shape, what we can do to try to detect what is the shape of the universe is to just try to detect those identical images. So we can either do it in catalogs of galaxies. This is very blurry, where we can look at the two-point correlation, and there are some spikes in the two-point correlation that characterizes a particular topology. Or usually the main method which is used is to look at the biggest scale, which is the cosmic microwave background, and to look at some periodicities in the scale with some circles that would, identical circles that would appear in this map. But as for now, we didn't detect anything. and we only managed to give a lower bound for the size of the universe, which is basically half of the CMB as for now. But it's an ongoing research, and it might change in the future and with better data, for sure. Regarding this second parameter, the special curvature, once again, we have no detection and only a constraint that this omega k is smaller than 10 to the minus 3. In terms of scales, this means that the curvature radius is of the order of the CMB radius, a bit less, like half, I think, something like this. Okay. So once again, the curvature is really small, but there have been a growing interest, I would say, in studying cosmological model that includes curvature, either for structure formation or for inflation. And this because we have increasingly accurate data. And for instance, with the Euclid Space Telescope or with future telescopes that aim at probing the azimuth of the CMB, we might increase by 1 order of magnitude the constraint on omega k. And so people tend to think that we should have like very accurate theoretical model to predict what would happen in that case for structure formation and inflation if we have a curvature. But as for now, again, no observation. Okay, so this is where we are observationally speaking. Now, as I said, I need to give some additional precision on the mathematics here. When I said that the topology of our universe, we have 3 types of families with different shapes. In reality, if we consider that our universe is 3-dimensional, so we don't do strings or whatever, for instance, so simplest assumption on the number of dimensions, then we have this nice classification, Thurston's classification, which says that any closed free manifold is classified into, it belongs to one of 8 families of topologies. And that a precise topology within this family is characterized by a choice of discrete group. The precise topology, I mean the precise shape we consider. By the way, that classification was conjectured by Thurston in the 80s, and it was proved by Perelman in 2003, in the same time he proved the Poincaré conjecture. So this is related to this. And so, graphically, this means that our universe, which is a free manifold sigma, can be described by a kind of a background manifold that is called the covering space, and the precise, which corresponds to the curvature, and the precise periodicity corresponds to a choice of subgroup here. Here it's a bit abstract, but we can come back to this picture where we had our spaces, Euclidean, spherical, and hyperbolic. Here it's a bit more complicated to draw something because they are a bit more exotic. For instance, this family corresponds to a universe which is basically flat in one direction and spherical in 2 directions. It's difficult to represent it with a 2-dimensional analogy. And the choice of subgroup, or choice of precise topology within this family corresponds to a choice of periodicity. So we have different shapes possible. Okay. And so any realistic cosmological model relies on using that classification. Now you might ask, okay, but why don't we use this? I mean, are they physical, or are there some arguments to say no, they are not physical and we have to use them? The answer is no. There is no fundamental reason to say that these are not physical topologies. The only reason we don't consider them is because of simplicity. They necessarily imply that globally the universe is anisotropic, and because we don't observe a global anisotropy, for instance, in the curvature or in the expansion rate, then we don't want to make the model more complicated, and so we usually do not include those possibilities. But there is no fundamental reason, there is no fundamental theory that says physically we cannot consider this. Okay. So this means that if we want to have a complete cosmological model, it should include, and a complete theory of gravitation, it should include, be well defined for any of these topologies. I will come back to this point later. Okay. One last thing I need to introduce is that each of these family is fundamentally characterized by a curvature. So we had it in the standard model, where we had like just a scar curvature and depending on the sign. Here you have some anisotropy, but it's qualitatively the same. You can attach to this family of topology a kind of a fundamental topological curvature, which is not necessarily the physical curvature. I didn't introduce any metric, any physical metric here. The moment I do it, that metric might have a different curvature. It's just that if our universe appears to be like of this type, then we know that there is fundamentally that canonical curvature that can be defined. Once again, let's keep this in mind. I will come back to it later.
Sorry, is this covering space curvature the Riemann tensor from the connection that the covering space is assumed to have an affine connection? You're going to discuss how this may be different from what you call here physical curvature, which is going to be somehow metric related and detached from the affine connection.
I mean, actually, it's defined from a metric. You have the let's say it's called a Thurston metric or the canonical metric, but it's just that it's another metric than the physical metric. Yeah. But
so it's a Thurston metric up in the covering space, and your quotient.
Yeah, your quotient
can be compared with the more usual concept of metric, which you're calling physical curvature. Well, the curvature from the more normal metric. Thurston metric upstairs.
No. I mean the Thurston metric. You can quotient it and define it there.
Yeah. And then you compare it with the metric.
With the physical metric, you can take the difference. Exactly. Actually, it will be more. What will be important will be more the comparison between the physical curvature and the physical metric. That's why I didn't introduce the canonical metric, but rather the canonical curvature. Okay. So that's it for topological introduction. Now let's dive into the motivation for that theory. And for this, I will consider that table, and I will spend most of this presentation just filling gradually that table. What we have here in the columns, we have the different families of the topology for our universe. The first line represents the relativistic regime of our theory of gravitation. And the second line represents the non-relativistic or Newtonian or Galilean regime of gravitation. The first line in our current paradigm is described by the Einstein equation, which is well defined regardless of the topology we want to choose. While the second line is described by the classical Newtonian equations or the cosmological one, here with this average density that is removed in the Newtonian equation. And because in those equations the special curvature is zero, then they can only define in a universe that has a Euclidean topology. This is due to a property that in those topologies you cannot have a zero curvature. And the last thing, we know that taking a limit of the Einstein equation where we take the speed of light to be infinite, it's quite easy to retrieve those equations. And so here you see that there are some holes in this table. The first thing, which is to two questions. The first one is, we have no equation to describe Newtonian gravitation in a universe with a non-Euclidean topology. And so this leads to the first question, how to define Newtonian gravitation, non-Euclidean Newtonian gravitation? How to generate Newtonian gravitation for any possible topology of our universe? And the second question is, if we can define something here, is it compatible with general relativity, again, when we take the speed of light to be infinite? And so here I will answer these two questions. We'll see what are the mathematical tools that we need, what are the different answers, and the answer to the second question will lead to that modification. Okay, so let's tackle the first one. And the first thing we need to answer is, what is Newtonian gravitation? If we say, okay, Newtonian gravitation is not just basically defined by a Poisson-like equation with zero special curvature, then that's it. We answered. If the Newtonian gravitation is defined by having zero curvature, then we are stuck to this topology, and that's it. But it's not very fundamental. We usually when we want to define a theory, start from symmetries. Here you can start from the principle of Newtonian gravitation, which is to say that basically it's a Galilean invariant theory. And say that, by definition, a Newtonian gravitation theory, regardless of the topology, should be a theory invariant under Galilean transformation. If you start from this definition, there is a beautiful mathematical object that can be used, which is called Galilean structure, that some of you know. So let's see what are Galilean structures. So on the left here I present Lorentzian structure, which are used in general relativity, where you have a four-manifold, space-time manifold, and you define on it a structure that is invariant under Lorentzian transformation and composed of a metric and a compatible connection. That metric gives the definition of space and time distances, and the connection gives the definition of physically how we compare between points in that space-time. And because of that structure, we have this slide cone and this absolute velocity. Now, similarly, we can define another type of structure that is rather invariant on the Galilean transformation. It's called Galilean structure, and is composed of two metrics, metrics H and tau, a space and time metric that gives independently a definition of how we measure space and time distances. And again, there is a connection that defines how we compare physics in different points. It's very interesting because here these are basically the fundamental objects that you can build from just the hypothesis of having a structure that is independent, invariant under Galilean transformation. And what is really interesting is that if you define such an object, you can define it in any topology and with any spatial curvature. It doesn't have necessarily to be flat. Okay. Now, from those connections, you can define with both of them a space-time curvature, which are different because you have different symmetries. And from the one on the left, the Lorentzian one, you get the Einstein equation. And what is beautiful with those objects is that by basically keeping that equation formally, but replacing the symmetry from Lorentzian to Galilean. So it's basically the same equation, which is called the Newton-Cartan equation. And then, spatially projecting this equation, you exactly retrieve the classical Newton's equations. So it's really beautiful. Here, basically, we say that we take general relativity and replace Lorentz invariance by Galilean invariance, and this is just classical Newton equations. So that shows that those Galilean structures are really powerful at describing Newtonian gravitation, because we retrieve them with that Newton-Cartan equation, and they are also powerful because they can be defined in any topology. So we can come back to this table here, where I fill in red all the new things. Here we just understood that this is the best way of describing those regions. And now we are in position to try to describe what is Newtonian gravitation for this topology. And so the question is, what is the equation that we should consider here using that object? So we can start with the one equation that we know, which is this Newton-Cartan equation. I say, okay, can we consider it on non-Euclidean topologies? And the answer is no, because from that equation, because it's actually compatible with, it's equivalent to Newtonian, classical Newtonian gravitation, the spatial curvature is 0, and so this imposes the topology to be Euclidean. So this means that if we want to define a non-Euclidean Newtonian gravitation, we need to consider a modification of that equation. And so the question is, what modification should we consider? The answer is that equation where we add here that red term, which is basically a spatial curvature. If you calculate now the spatial curvature that is induced by the Galilean structure, it's not anymore 0, and it's compatible with, here I took the example of a spherical or hyperbolic topology. Now you might ask, okay, from where comes this modification? So there are a few hypotheses there. The first one is you want that term to be 0 in the Euclidean case. To retrieve classical Newtonian theory in the Euclidean case, so it's the case here. This k is the curvature and it's 0 in the Euclidean case. You want it to be present in vacuum, in the sense that you want, even in vacuum, that Newtonian gravitation should be well defined. And you want something that is second order or less in the derivative of the metric, because you don't want a higher derivative theory. And the reason is that there is no, actually, for me, I see no reason why Newtonian gravitation on, let's say, a spherical universe should be a higher derivative than Newtonian gravitation on a Euclidean universe. And so with those hypotheses, you end up with that equation, which might seem to you, as for now, a bit abstract, as the Newton-Cartan equation is. But once again, we can take the special projection. And what, to my opinion, definitely shows that this is the right answer to what is Newtonian gravitation on any topology, is that the special equations are exactly the same as the classical Newton equation, with the only difference that in the special derivative, the special connection, you have it's related to a metric that is curved. And so in particular, what is beautiful is that with this term, we retrieve the Poisson equation with, again, the difference that the Laplacian is curved. And so it's very nice, because if at first you would have say, okay, what heuristically should we guess to be Newtonian gravitation in a non-Euclidean topology? You would have said, okay, it's just the Poisson equation with some curvature in the Laplacian. And what is beautiful is that if you use those fundamental objects that are Galilean structure and basically minimally modify the equation, it's directly what you get. Now, just a little thing that we can do before coming back to this table. We can actually, that Poisson equation, we can solve it the same way we solve it in the classical case, and we get the Newtonian law in 1/r for the potential. We can solve it for different topologies. And what is beautiful is that, so we consider one mass point in the center of the universe that is spherical, that is hyperbolic, or that is flat, but which is a cube, a torus. What is beautiful is that in any case, close to the mass point, so at a distance small compared to the size of the universe, we always retrieve Newton's law, and there are correcting terms that depends on the topology. You have none if you are on an infinite space, and if you are still flat but on a periodic space, you have some correcting terms that are actually considered in cosmological summations. And if you have some curvature, because you are spherical or hyperbolic, you have other types of correcting terms. But what is important here is that basically Newtonian gravitation always predicts at small scales Newton's law for the potential, regardless of the topology of our universe. Okay, so we can come back to this scheme again, and we managed to fill this hole here. Imagine that we need to consider the equation to define Newtonian gravitation. Now the last thing that remains to be done is answering that equation. Can we retrieve this from a non-relativistic limit of general relativity? And here, once again, we have to understand what do we mean by Newtonian limit, in how do we define Newtonian limit. So in the literature, in textbooks of GR, there are a lot of ways it's defined, and most of the time, basically it's a kind of fixed field limit around Minkowski or around some flat FRW. The problem if you do this is that if it's around Minkowski, by definition it's spatially flat, and so you cannot define such a limit other than in a flat topology. So rather, we can again use those very beautiful objects that are those structure here and define a Newtonian limit with respect to them. Define in a sense Newtonian limit as being a limit between two symmetries, Lorentzian and Galilean symmetries. This is something that was first proposed by Künstler, who developed a lot this Galilean structure. And so I will not enter into the full details of the ansatz, which is you make some assumption on the Taylor series of the metric, the Lorentzian metric as function of the speed of light. But conceptually, what you have is that you have a space-time that is equipped with a Lorentzian structure that depends analytically on the speed of light. And when you take the speed of light to be infinite, in the limit, that space-time becomes a spacetime equipped with a Galilean structure. So you change from Lorentzian to Galilean symmetry. With the usual interpretation that you change basically how you define physical measurements from light cones to that you flatten to those spatial hypersurface and, let's say, preferred space on which you define measurement. Okay, and there are two interesting things, is that once again we define this limit with respect to this structure, to this symmetry, and so this is something that can be defined regardless of the topology, regardless of the spatial curvature. If that space-time is like R cross S3, R for time, S3 for the space, this is a limit that we can define there. So it's very suited for our purpose of analyzing the Newtonian limit in different topologies. And the second point is that here you see that this is something that happens in the manifold. So that limit changes the structure, but doesn't change the manifold. And since the topology is a property of the manifold, this means that topology isn't changed by this limiting process. Once again, let's keep this in mind.
Sorry, could I just ask, was Kunzler in 76 aware that the limit manifold need not be spatially flat? Because when you're saying no constraints on spatial curvature, you're saying something which for us philosophers, at least me, slight knowledge of this topic, mostly for most of us through David Malamant, we tend to have articles suggesting that the spatial slices in the limit manifold must be geometrically flat.
Spatially flat.
Yeah. But you're saying this is not so, and I'm wondering, is Kunzler in fact aware of it?
That's a good question, yeah. And there is only, to my knowledge, there is only one paper that like basically describe that modify Newton-Cartan equation that describe where you add some curvature. And it is actually in that paper. So with that paper, he was totally aware. Though when he took he defined the limit, and he took it from, then he took the limit of the Einstein equation. He wanted to retrieve the Newton-Cartan equation, so he wanted to retrieve spatial flatness. So he didn't try to have a field equation without spatial flatness. Actually,
he was kind of aware of this option, but
yes, because
the overall kind of narrative of the
exactly
is to set this option aside and to obtain the normal flatness.
Yeah. In this paper, it's a remark. He has a 5-line remark where he says it's a possibility to have a non-zero spatial curvature, but then he discarded it. Thank you. So, back again to the table. So here what we feel is this thing where we understood that this is the right way of defining the limit. And again, this is a definition that if we don't consider any field equation, geometrically doesn't impose anything on the topology, and so this thing can be defined everywhere. Now the question is, you assume you have a solution of the Einstein equation. You start from this. Can you take the limit of such a solution in the case you are not on those topologies? You are on those topologies. So let's do it. We start from the Einstein equation. And what is the result we have? That we always get, we don't assume anything on the topology first. We just start and we make a local calculation in a sense. We always get this Newton-Cartan equation. The hypothesis for that result is first either in vacuum, so in vacuum you don't have the right-hand side, or let's say reasonable matter fluid hypothesis on what is on the right-hand side, this matter here. If you consider a scalar field, for instance, this is also a result that you have. Basically, you have the Newton-Cartan equation. And so here, because you have this Newton-Cartan equation, we know that at that level, space is flat. Doesn't mean that the solution of GR that you start with is spatially flat. We know that at that level it's flat. But if you remember, that limit is a limit of structure. So it's flat, so it means that the topology in the limit is necessarily Euclidean, the spatial topology. But because we don't change the topology with this limiting procedure, this means that it had to be Euclidean all along this process and at the starting point. So in other words, we have this theorem that a solution of the Einstein equation admits a Newtonian limit only if the topology is Euclidean, with those hypotheses for sure. And so coming back to this table, this just means that basically that word here, that beautiful word, I'd say, is not compatible mathematically with general relativity. So here we answer that second question. So what do we do now? We could say, okay, there is basically, we can define Newtonian gravitation for any possible universe. It's uniquely defined, it's quite beautiful because we get the Poisson equation, but it's just not compatible with GR, so we can just, okay, it's maybe just a theoretical trick, but physically it means nothing, maybe, because it's not compatible, and we stop here. So maybe you like this interpretation, maybe I don't like it, and rather I prefer to interpret this result as an issue, a problem for general relativity that has to be fixed. And why is that? Because this means that if our universe is, for instance, spherical, then both the use of the Einstein equation to describe the expansion or whatever, and the use of Newtonian gravitation to describe solar system dynamics is, strictly speaking, mathematically incompatible. And imagine our universe is spherical. This means that when we describe it with GR, then we are describing it with a theory that doesn't include the theory that we use to describe the solar system. So you might say here, yeah, but when we use Newtonian gravitation to describe the solar system, we actually use those equations here. So we use Newtonian gravitation on a flat space, which is compatible with GR, so there is no problem. But it's not the case. What do? We use basically Newton's law. If you remember, Newton's law is present regardless of the size of the universe, and as long as the topology of the universe, as long as the system that we study with Newton's law is small compared to the CMB, which is always the case actually, then we are just using Newtonian gravitation, but we don't know which one it is. Because we don't know the topology of the universe. We are just using Newtonian gravitation, but not necessarily the Euclidean one. And so, from this fact, it seems a bit restrictive to now consider a relativistic theory that would be only compatible with that type of Newtonian gravitation, only compatible with Newton's law, but in the Euclidean case. Okay. So we can discuss this because it's the main point of my what comes next. To my opinion, this leads to considering a new principle. I don't know if principle is the right word, but this thing, which is that we should require that any relativistic theory of gravitation should admit a Newtonian limit for any topology. And if we assume this fact, then this means that we want this to be compatible with what's above, so we ask for what is the modification of general relativity that admits a limit regardless of the topologies. Now, okay, you might not be convinced by the argument I use, but still this is an interesting question and to ask, and let's see what is the answer. So we want to modify the Einstein equation such that it has its limit. What is that term? And more than this, what constraints can we put on that term to try to find what it is? So there are a few of them that, to my opinion, are quite natural. That term should be 0 for Euclidean topology, because as we saw in the Euclidean case, there is no problem. The limit exists. It leads to classical Newton equation. Because we add this term for topological reasons, it seems logical to say that it should depend on the topology, and more precisely on the family of topology, not the precise shape, but rather the family. Second, we don't want to increase the complexity of the theory by having a, let's say, third or fourth order derivative theory. Because once again, at the Newtonian level, all the theories are second order theories with the Poisson equation. And so because of this, there is a theorem, the Lovelock theorem, that says that the only second order theory in which you have a Lorentzian metric is general relativity. So this means that if we still want a second order theory that is not GR, we need to introduce an additional field. And so because we would introduce it for a topological reason, what we can say is that, okay, we need to introduce an additional field, kind of background field, for instance, that depends on the topology of our universe. And the last one for sure is that we want compatibility with the limit. With this, I'm not sure there is a single solution, at least I didn't derive it, but I found one solution which, to my opinion, is the simplest, in the sense that it doesn't add any new parameters to general relativity. And that solution is that equation that I showed you in the first slide. What do we have in this theory? We have still the physical Lorentzian metric, G, and its Levi-Civita connection and its tensor. But we have a second field, which is a connection, fixed background, we can say connection, that is non-dynamical, which comes with its let's say reference Ricci tensor. And the equation is changed such that on the left-hand side, rather than having just the space-time physical Ricci tensor, we have the difference between the space-time one and this background Ricci tensor. Now, this is an equation that was proposed by Rosen in the 80s, the same Rosen than Einstein-Rosen bridge. Same equation, but different choice for this term, which I will present there. The reason Rosen proposed it was to try to solve singularities of black holes or Big Bang. And so the way he chose this term was totally different, fundamentally different from mine. So this is the only similarity that is between my approach and his approach. And so, as he said, we introduced this for topological reasons. And in which sense does it depend on topology? The following. The way that term is defined is the following. That it's basically a background curvature that is flat in the time direction, we can say, and that is non-flat in the space direction. And this non-flatness, the spatial curvature, reference curvature we have here, is exactly the canonical curvature of the family of in which the universe belongs to. So if you remember, there was this technical slide where I said we have 8 families, and related to your question, there is for each of them a canonical curvature that defines those families, and this is what enters there, and so therefore what enters into that term. So it's for this reason that this term depends on the topology of our universe. And so you see, for instance, that it is 0 in the Euclidean case, and so this equation, this theory, and general relativity are equivalent for Euclidean topology, are not changed in that case as we wanted, and they differ only for any other type of topology.
It's also quite your equation has this intuitive idea for me, at least. May I ask if it's fair? The stress energy tensor sources the difference between the Ricci.
Yes.
So it's not just background and non-dynamical. It's also it's like a standard or a yardstick.
I come back to this just later. Yeah, that's the
baseline on which you look at the spikes in Ricci.
That's the right imposition. Right. Okay, and so for good to say, you can check. I will not show here. But basically, you check every hypothesis. Okay. Once again, it's a very simple modification because there are no additional parameters. There is this term here, but the moment we say we want to study a spherical universe, it's fully fixed. So the only parameters there is the choice of topology, which is in any case present in general relativity. So in this sense, we are at the same level of complexity than GR. Okay. Coming back to the table, so this just means that we show that for all of this to be fully coherent, we need to consider the equation. Here I actually merge those two equations into this one, as actually that term that we added in Newton-Cartan equation is basically the same that we had here. And this is basically a complete picture of the relation between a relativistic regime and non-relativistic regime of gravitation with any possible topology. So with this, I think we can make a interesting analogy, comparison, I mean, with the Mendeleev table, where we had some holes in this table, like where we classified with the topology, and we filled those holes. And we said, there should be something there, and we actually found that, okay, we can actually have this Newtonian gravitation there, and it's basically uniquely defined. So the same. And more than this, when Mendeleev made this classification, he made some mistakes because he classified them by mass. And so even he said there are missing elements, the existing elements were kind of slightly modified later to be classified with the number of electrons that was not known at that time. And so it's as though somehow what we did, the known element which was general relativity, we actually kind of modified it to make the table fully coherent. That's where the comparison stops, I think. Okay, so now coming back to this theory and to your question, it's nice we modified the Einstein equation, but it's always good to understand what we did and just not work with the mathematics. To understand, to have an interpretation of what we did with this modification. And there is a nice interpretation, which is just summarized, actually. For this, let's start with GR and the usual way we present this equation, which is to say that vacuum, so where the right-hand side doesn't source the space-time, it's zero. Space-time is richly flat. The role of matter is to curve that space-time with this usual path. Here, in this theory, which I tend to call topo-GR, by the way, in vacuum, space-time is not necessarily richly flat. The space-time curvature, physical one, is equal to the curvature that is imposed by topology. So in vacuum, we rather have this picture, and then we see that the role of matter totally changes. It doesn't curve space-time, it only induces a deviation, not necessarily small, a deviation from like the fundamental curvature that is imposed by the topology of our universe. It's more that picture that describes this theory. How much time do I have left? 5, 10 minutes?
At least 10.
Okay. Plenty of time. Okay. So, this is how we can understand this theory. Now the question is, we saw this motivation, quite strong to my opinion, but it depends on how you like the interpretation I made on this incompatibility result. But still we can say now we can forget about the motivation, we have that theory, what are the consequences? As I said, this is something I already studied, a bit for black holes, and essentially for cosmology. Why cosmology is more interesting? Because since it's a modification that depends on the topology, and we saw in this observational status that the topology of our universe is necessarily really big, so we expect the observational consequences of this modification to be only seen at large scales. And so for this, what we can do is just derive the homogeneous and isotropic solution of that equation. I recall on the left-hand side where we have GR. So here I take homogeneous and isotropic, so we are in the first free case, Euclidean spherical hyperbolic. We have that curvature that is present in the expansion laws and with different expansion scenarios. Here, because you have this term here, somehow it will add an additional omega parameters, would be the omega parameters of this thing, an additional contribution to the expansion. What you can show is that it is exactly opposite to the contribution of the curvature. which means that the expansion law in that theory is this one, in which you don't anymore have the curvature, and so it's fully independent on the presence of spatial curvature. I sometimes say that, as a title here, it's the expansion becomes blind to the spatial curvature here, dynamically, but the spatial curvature is still there geometrically to distort, change the measure of distances. And so we have this evolution where the evolution of the expansion of the universe is the same regardless of what is the topology, the spatial curvature of our universe. And in particular, we don't anymore have this recollapse there. And so here we have two things. We saw in the Newtonian case that with that theory, by definition, it behaves nicely with respect to Newtonian limits regardless of the topology, while GR didn't. You have this incompatibility in non-Newtonian topologies. And here in that case, we have this dynamics of the universe that is the same for any topology. And again, in GR, everything is really different depending on the topology. And so we can have this statement, which is that it seems that here the behavior of gravitation is more universal, is more the same with respect to topologies than in GR. And so why I advertised since the beginning this theory as being a theory, a modification that depends on topology, at the end, between GR and topo-GR, it's rather GR in which the gravitational phenomenon depends the most on topology. And in topo-GR, my theory here, gravity is basically kind of universal, behaves the same regardless of what topology we choose for our universe. Okay, I will finish with that slide, basically. But as I said, there are some ramifications there. Something I didn't have time to explain, which is this beautiful result that I had here, which is that if you go further and you calculate the perturbation around a homogeneous universe, and you in particular study inflation in the context of that theory, then you get actually an additional motivation for why it's better behaves than generativity. To make it quick here, the statement is that in GR, this plane homogeneity of the universe, you assume inflationary phases in the early universe. And if you assume that at that state of the universe, the state of the matter was just the simplest state possible, a scalar field, then beautifully and with the simplest assumption, then you manage to show the homogeneity of the universe, solve the Hubble the horizon problem, etc., etc. This simplicity of inflation is what makes it success. But it's only the case in GR if you consider a flat space. The moment you want to do inflation in a curved space, so curved topology, this simplicity and natureness of inflation is lost. You need to have more fine-tuning, you need to introduce additional parameters, or actually change the mechanism that creates the initial the parameter power spectrum. What is beautiful if you want to try to do inflation in that theory with a curved background is that it's as simple in nature as flat inflation in GR. So you keep the simplicity regardless of what topology. And once again, it's another example of this statement. I said that it's really universal. Basically, everything is the same in topology. While in GR, the moment you consider curved topologies, then most of the time, everything becomes more complicated, kind of less natural. Okay, so that was this recent result I had. Now, in my opinion, the best perspective on top of analyzing consequences for black holes or cosmology would be to try to add some additional motivations. And the best motivation would be one from quantum gravity, would be a fundamental motivation rather than a purely mathematical one like this one. And for instance, if we could, with some quantum gravity approach, show that in the classical limit, actually this is a term that generically appears if we consider the classical limit in that or that topology, that would be a strong motivation. So that's a future prospect. So now if you want to take away two takeaway messages. First one is that in that theory, matter does not curve space-time, but it only induces a deviation with respect to the curvature that is imposed by the topology. And this second message, which is that, yes, it's a modification depending on topology, but actually the gravitational phenomenon is more universal in topology R than in GR. I thank you for your attention. And for this 5-minute pause, I have some sweets from Lyon, if you
We'll take a 5-minute break and eat some sweets.